aluminium will form Al2O3, and like in bulk form they are unreactive. Why they are unreactive? Because for example, boron, if you take boron, if you consider, okay, we have seen that boron that exists as B12 units, which are icosahedral, we have seen that. So it doesn't react very quickly. Okay, so boron is unreactive in crystalline form. It is extremely hard, right? Aluminium, the reaction stops. We have discussed that why it stopped, because of the formation of a hard layer of Al2O3 on the surface, which stops the reaction of aluminium. Okay, now move ahead, and then we move to the reaction with nitrogen. Okay, so what we observe in reaction with nitrogen is, let me write it very quickly. Reaction with nitrogen. So what will form? Tell me. So whenever we have oxygen, we form oxides, right? And whenever we have nitrogen, we form nitrides. Okay. So nitrides actually boron form nitride at a very high temperature, but the crystalline form of boron will not react, right? This is boron nitride. This is covalent. And it has structure similar to the structure of graphite. So what is the structure of graphite, you know, Fatima? What the structure graphite is having? Tell me.
I don't know, sir.
Okay, okay. No problem. Having boron. So ring is there, and the rings are not independent. They are actually making a sheet-like structure. Sheet kind of thing. So actually we are having a covalent structure, right? This is known as a covalent structure. A sheet like it is covalent in it. So there are more sheets. This is one sheet, complete sheet. Graphite is also having a sheet-like structure, but the graphite, the sheet are made up of carbon atoms only. But in boron nitride, they are made up of, and you have one sheet below another. Okay, all the atoms will be in the sheet. There will be one more sheet-like structure. Okay, and these actually, it is a slippery white slippery solid. Why? Because these sheets can slide on one another. Okay. Similarly, you have aluminium. Aluminium can form nitride. That is at a very high temperature, ALN. So this is +3 and this is -3, right? Aluminium is a metal. Okay. So, and because it is a metal, means it is forming an ionic kind of thing. +3 on aluminium and -3 on nitrogen nitride. And the proof of this +3 and -3, whatever the ionic compounds are there, upon putting water, they undergo hydrolysis. So water is H plus and OH minus, right? So put H plus on N3 minus and OH minus on Al3 plus. So you will end up with AlOH whole thrice and ammonia. Ammonia is we discussed last time. Ammonia is a colorless gas having pungent odor. It is having a basic nature. It will turn red litmus blue. Clear? Rest elements, they do not react actually with nitrogen. For example, you have gallium, indium, and thallium. Okay, they do not react with enter. Is it clear, Fatima? Ionic nitride means ionic nitride. This is always with all the compounds. If it is an ionic compound, it can react with water. Okay, it will undergo hydrolysis. And boron never form any ionic compound. Boron always form covalent compound, right? Oxides we have seen, and in oxides, what is the formula of oxides and hydroxides? Oxide oxygen is -2, we have seen. So we cross multiply the number of ions with their charges. So oxygen is -2, so I multiplied by boron. Boron is +3, so I multiplied by 3 oxygen, but number of oxide ion by 3. Al2O3. Just a quick recap. So these are the oxides, okay? And this is acidic in nature, okay, because it is non-metallic oxide, so it is going to be acidic in nature, okay. And aluminium and gallium are amphoteric. What do you mean by amphoteric? Yeah, Fatima. Yeah, tell me. Amphoteric, acidic means it can react with base. Amphoteric oxides are those oxides which can react with both acids as well as bases. Okay. And we have seen the thallium will form 2 oxides. Okay. Thallium 1 oxide and thallium 2 oxide. Thallium +3 and thallium +1. Is it clear, Fatima?
Yes, sir.
Now we move with the reaction with acids. In acids, actually, there are acids which are oxidizing acid. Reaction with acids. Oxidizing acids means which can oxidize, which can give oxygen. Okay. So when we look at reaction with oxides, actually boron does not react with normal acids. Boron does not react with non-oxidizing acids, okay, like HCl or acetic acid, vinegar is there. These are non-oxidizing acids, okay. Oxidizing acid, strong acids are H2SO4 and HNO3. So boron can react with oxidizing acids. And what are these oxidizing acids? These are actually HNO3. HNO3 is a very strong acid, and H2SO4. Okay. So what is going to be the reaction? So boron is going to give the 3 OH group. Take the 3 OH group from OH of HNO3. Okay. HNO3 you can think as OH and NO2. Those OH group attached to boron, it formed BOH hydrides. And what is left behind from the acid? NO2, which is a reddish brown color gas. So boron get oxidized because oxygen are added to it, and it forms a boric acid. It is also written as H3BO3. Upon reacting with oxidizing acids, boron forms its own acid and it reduces another acid, HNO3. Okay, so it itself forms H3BO3. Is it clear, Fatima?
Yes, sir.
Okay, let's move to the next slide. Okay, I hope you have copied everything.
Yes.
Okay, good. So what happens if you react it with H2SO4? H2SO4 is also a very strong acid and it has 2 H groups. Okay. So those OH groups come on boron. Okay. And boron forms its own acid, which can be written as BOH hydrides or H3BO3 orthoboric acid. And H2SO4, because the oxygen is removed from H2SO4, the H2SO4 is reduced to sulfur dioxide. Okay. So sulfur dioxide is a gas which is having a smell of sulfur that comes out. Okay. Now the next thing is aluminium. Aluminium is there. Aluminium can also react with these acids, right? Like HCl With dilute acids, it can react very quickly. It forms AlCl3. And it gives off hydrogen. So all the metals do that. Metals have a very good reducing character. Okay. And because of the reducing character, they can give off their electrons, and when reacting with acid, the electrons are taken by the H plus of acid and the H plus changes to hydrogen. Clear?
Yes.
So hydrogen is liberated. Okay. Now this is the reaction, but with HNO3, the reaction stops. Reaction stop. Why it stops? It stops because of the formation of layer of oxides on its surface. Okay. And this layer of oxide of Al2, oxide, aluminium oxide, is very hard. And it is very, very hard. And because it is hard, it forms a layer, thick layers on the surface, which prevent the reaction of aluminium. Okay, inside aluminium doesn't react because of the formation of this hard layer on the surface. Okay, now comes the reaction of with bases. Reaction with bases or alkali, and the most common alkali is NaOH, right? Boron, we know that it is very unreactive because of its that complex structure which contain B12 unit inside it, icosahedral, which actually doesn't allow the boron atom to separate easily and react easily. So boron react with NaOH, but the temperature which we require, first of all, we can take amorphous form of boron, powdered form of boron, the boron which is not crystalline. Okay, crystalline always will have difficulty in reaction. Okay, so boron, what you do is you can take the powdered form, it can react with NaOH, and we also keep the temperature very high. If you keep the temperature very high, and that is around 500 degrees Celsius, then this boron can react with NaOH. Okay, so actually or it can react with NaOH, or you can take a more strong base also. KOH is more stronger than NaOH, so you can take KOH also, and that can react more easily with boron because it is stronger base as compared to NaOH. The reaction occurs because this is a very high temperature, and this temperature actually lead to the melting. Okay, fused, or you can write it as fused condition. Melted base, you can take it. It is a very strong condition. Okay, so then it can react with boron, and the boron is going to form the acid. Let's think that acid, but acid doesn't exist in basic medium. It is going to form a salt, A3BO3. This salt is going to form, okay, and hydrogen gas is going to come. So we can balance it. Okay, that's how the reaction occurs. So it forms S3. Earlier in the acidic medium, we formed H3BO3. Okay, this was the orthoboric acid of boron. But in basic medium, all the H plus of the acid will be removed and its place will be taken by potassium and the hydrogen gas will liberate. Okay, this is known as potassium borate. Okay, and the next thing is aluminium. Aluminium also is a very good reducing agent. In fact, aluminium can react with NaOH. Okay, and it liberates hydrogen. So aluminium is a very, very strong reducing agent. So aluminium, NaOH, okay, or it can react, you can react with KOH also. This is a very famous reaction. You might have studied it in your junior classes also. Okay, H2. So actually it forms hydrogen gas. It forms a salt, first of all. NaAlOH whole 4. In the aqueous medium, if it is there, it is NaAlOH whole 4 or NaAlO2. And hydrogen gas will be liberated. Okay, clear? So now we need to balance it and we can balance it. This is a very famous section. Aluminium is a very strong reducing agent and its reducing character is because of the liberation of hydrogen. Aluminium in basic solution is a very, very strong reducing agent. Okay. So actually you can, what you can do is 2 aluminium, 2 NaOH and you can take 6 water. Okay. So actually aluminium and 2 NaAlOH whole 4. Okay, and then you can have H2 coming out, you can have 3 H2. You can balance it. No need to balance it. In fact, just you can simply mention that hydrogen gas will be liberated and aluminium is +3. So 4OH minus going to join to aluminium and aluminium, this whole thing in the square bracket will have -1 charge. Okay. So there are going to be 8 hydroxide ions total. So 6 from water and 2 from OH minus. And 6 from water, 6 hydrogen will be there. That I've written as aluminium will give its electron and will lead to the reduction of H plus ions to hydrogen gas. So metal liberate hydrogen. Okay. Right? Clear? So this is a very important thing. I hope you understood it. Clear? Any doubt on this, Fatima?
No,
Yeah.
sir.
Just try to balance the equation that aluminium is going to give 3 electrons, boron is going to give 3 electrons. Okay. And it will take hydrogen. Okay. It will be taken away by H plus and that H plus will come out at hydrogen. That you should remember. Right? Now there is a reaction with halogens. We have seen reaction with oxygen, nitrogen. We have seen reaction with acids, bases. Bases actually, boron is acidic oxide. It will react with base KOH and it is going to form its salt. Aluminium will also react with the base and it is going to form a complex. This is a complex actually. Okay. and hydrogen gas will be liberated. Similarly, gallium is also amphoteric, so that also will react in the same manner. Okay. Now the next thing is, let's move on to the next slide. Next thing is reaction with halogens. Okay. So these element halogens are fluorine, chlorine, bromine, and iodine, and they are very reactive. Okay, so they are very reactive and they can react very quickly with these elements. In fact, halogens can react with most of the elements because of their reactivity. So next thing is reaction with halogens. Okay, so metal plus halogen, fluorine exists in gaseous form. Okay, and chlorine is also gaseous, bromine is liquid, iodine is solid. Out of it, the reactivity decreases down the group. Mostly these fluorine, chlorine are very reactive. Okay, so actually this is going to form trichlorides, MX3. Metal, it is going to form metal or a non-metal boron. It is upon reaction with halogen form tri-halide, and this X can be FClBri. It is halogen. So let's analyze the structure of boron halides. So boron halide, it is going to be like this, right? What is the characteristics of these halides? If you look at the number of bonds, they are having only 3 bonds, means 6 electrons are there. And there is a vacant orbital because these second bid element can make 4 bonds. And because they have only 3 electrons, that's why they have made only 3 bonds, but overall they can make 4. And because of it, there is actually a vacant p orbital present on these halides. So I should say boron halides act as Lewis acid. What do you mean by Lewis acid catalyst? Yeah, Fatima. Mean the catalyst which can take away the electron pair. Okay. So actually they are such catalysts are known as Lewis acid catalyst. Okay. And why they can take away electron pair, why they can take away, because they have a vacant orbital and they can join, they can accommodate one atom, one ion which can come and join with the electron pair. Okay, so that is the reason. So suppose how do I prove that boron halides are Lewis acid? So what I can do is I can take BX3. BX3 is any of the halide of boron, and this is the empty box which I have made. Empty box means it has empty p orbital, and I can react with the NH3. NH3 has a pair of electron which is not bonding. That is called lone pair. So this can come and join on boron. So So I can write it as BX3. I can put an arrow from nitrogen to boron, indicating that nitrogen has given its pair of electron to form a bond with boron. Or if I'm not putting an arrow, I need to put charges, need to show charges, because nitrogen has donated its electron. So nitrogen will have plus charge and this is have minus charge. So this is Lewis base, right? And this is Lewis base is the one who can give pair of electron, and this is Lewis acid. Fatima, is it clear?
Yes, sir.
Any doubt in this? So, any doubt? Tell me.
No, sir.
Okay. Just little bit idea is required. Okay. No need to get into the detail. Just because they do not have complete bonds, they do not have 4 bonds, group 13 elements, they can accept electron from any other atom, and that atom can come, that molecule can come and give them electrons, and they can, that another molecule can join itself to boron. Clear? And this is known as Lewis acid Lewis base reaction. The one who gave pair of electron, that is called Lewis base, and the one who accepts it, it's known as Lewis acid, right? So this is actually the reason. Similarly, aluminium halides are also used in organic. Okay, you might study it in this hydrocarbon. We will be studying it very soon. That these organic halides, there is a reaction Friedel-Crafts reaction. Have you studied it in your school? Friedel-Crafts alkylation in hydrocarbon. So there they use aluminium AlCl3 only. AlCl3 also behave in the same way. AlCl3 is a Lewis acid. AlCl3 or gallium chloride, all of them, even BCl3. These halide act as Lewis acid. Why do they act as Lewis acid? Because these have vacant orbital and they can accept a pair of electron, okay, from that another atom. Okay, is it clear? Any doubts in this? Okay, very good. So let's move ahead. Let's move to the next topic. This is halide. Halide structure is clear. Boron form covalent halide because I'm showing bonds. Aluminium. In aluminium actually is more electropositive because it has more down the group metallic character increases. Sorry, and the tendency to form cation increases. So AlF3, I will write in a general manner. These are covalent. They are covalent. Okay, right? So these are halides which have a tendency to accept electron from any other atom or molecule, which is known as their Lewis acidic character. So let's move to the next slide. Just now, sorry. Now we will look at their reaction with hydrogen. Okay. Before proceeding ahead, let me tell you a little bit more about aluminium halide. Do you remember that last time we have seen beryllium halides? They were having long chain polymeric structure. Do you remember that? In the same way, aluminium also exhibit the same kind of bridge bonds. It can form same kind of bridge bond and it can form same kind of polymeric halides. So monomer, but this is valid only for covalent molecules, not for ionic molecules, not for ALF3, which is ionic. Chlorides are mostly ionic in nature. Okay, because chlorine is very electronegative, it has tendency to pull electron, and because of its tendency to pull electron, it actually become minus and Al become plus 3. Okay, so what are the structures of these? Let's see. Monomer I have already shown you. This exists as a covalent molecule AlCl3. Okay. And this is planar, trigonal, planar, having 3 bond at 120 degrees. It is planar molecule. It acts as a Lewis acid. That's also what we have seen just now, because it can accept electron pair because it has a vacant orbital. It can form a dimer. Dimer, how it is going to form? Aluminium is there, and these two AlCl3 molecules can come close to one another. And if some other molecule is not present to give them electron pair, these aluminium chloride molecule, they come together and they themselves give their electron pair to one another. Okay. So that's how they form a diamond. This is not a planar structure, right? Because in this, the aluminium is sp3 hybridized. So the chlorine on the outer side are like this in the horizontal plane, and the chlorine in the middle are in the vertical plane. So it can have polymeric structure also in a same way. other aluminium molecules, AlCl3 molecules can join together and they can form a polymeric structure, and that it's, we can write it as AlCl3n. Okay, and this polymeric structure is going to exist only in solid state. Because in solid state they are going to join together and molecules, the forces will be very high and they are going to combine together, and that's why it is, if you heat it, it is going to melt away, and it is all the molecules which were combined in a polymeric form, they are going to break into dimeric form, and if you heat it further, it is going to form a monomeric form. Okay, so this is AlCl3. Now let's move to hydrides. Hydrides mean what? Yeah, Fatima.
Reaction with
Yeah, hydrogen. Yeah, exactly. Reaction with hydrogen lead to the hydride formation. Okay. So actually, hydride formation, same way, because these hydrides are also electron deficient. All of the group 13 element will be electron deficient hydride. Okay. And because they are electron deficient, they are going to fulfill their deficiency by combining with each other. When they combine with each other, they themselves share their electrons. The way in which we have seen it in AlCl3. In AlCl3, two molecules join together. The chlorine lone pair, the chlorine atom gives its lone pair to another AlCl3, and in turn it accepts the lone pair from that AlCl3. Okay. So hydrides, you have boron hydride BH3. So this is monomeric form. It is going to be electron deficient, that we know, right? It is an electron deficient hydride. We know that. So how come it can fulfill its deficiency? Because it is having only 6 electron. So how come it can overcome its electron deficiency? By combining with each other. Okay, so two boron molecules combine with each other and they form a dimer, right? They form a dimer. Dimer is B2S6. It is known as Diborane, right? And what will be its structure? Same way. Dimeric structure we have seen over here. Because two molecules are going to combine with each other, what we are going to do? We are going to this whole thing has 2 electrons, and these 2 electrons are now getting distributed through to the other, through hydrogen it is getting distributed to other boron also. Okay, in this we have seen the same way in beryllium hydride also. So it is going to form a dimeric structure. This is known as diborane. It is also, it will also be not planar. Just like AlCl. Non-planar structure. Two hydrogen, if you consider them in a vertical plane, the other 4 hydrogens will be in the horizontal plane. If you react this with a molecule, okay, like who has a lone pair to give it to boron, Then these two boranes get separated because there is some other molecule which is coming and getting joined to each and every boron by giving its electron pair. Now these two boranes need not to stay together to share their electrons, because there is some other Lewis basic molecule which is coming in and which is giving them electrons. So that is a better option. In fact, if you look here, and it is just like a compromise because these two borane have come together and there are no extra electrons which are coming in from outside. Actually, these two borane molecules, they are sharing their own electrons only. And that's how they are joining together. The electrons in the hydrogen bond which were there initially, they are getting distributed over to other boron. And similarly, this boron, the boron on the right hand side has also shared its boron hydrogen electrons with the boron on the left hand side, and that's how they are going to join together. That's it. But it is, they are actually not getting any extra electron from outside from other molecule. So what we can do is, if suppose some other molecule is coming in, then they will part away, they will get separated and they will join themselves to that other molecule who is sharing their electron, giving its electron to them. So, let's discuss. I'm moving to the next slide. Is this clear? Any doubt in this, Fatima?
No, sir.
Okay. So let's take one example of this, and that example is NH3. NH3, we have seen that NH3 is having a lone pair. Okay, we have seen over here also. Okay, NH3 is having a lone pair, right? So NH3 can give its lone pair to boron. And if NH3 is coming, giving its lone pair to boron, then these two boranes should not, no need to stay together. Okay. So the next thing is reaction of diborane B2H6 with NH3. And what the reaction is going to be? The reaction is going to be very simple. Okay. We have this molecule B2H6 molecule. I'm writing the structure. Okay. I'm writing this structure so that we can understand. And I take two NH3 molecule. These NH3 molecule have lone pair which they can give to boron, and now these two boranes should not, there is no need for them to stay together, so they will break. Okay, because ammonia NH3 is giving them electron. Okay, so this is NH3, this is NH3, right? This is the cation. Okay, and the one who, this is actually known as unsymmetrical cleavage, because ammonia come and join to them. Okay, and both the ammonia molecule come and join to one boron, and another boron permanently takes away hydrogen with it. So now both of them have complete 4 bonds. Okay, and they will exist in this manner. In the presence of NH3 only it will happen. They will be separated from one another because NH3 is giving them electrons. So now there is no need for them to stay together. Clear? These are bridge bonds. Initially, how many electrons were there in each bond? Suppose this bond is there. There are three atoms. Okay, three atom, boron, hydrogen, and boron. Three atom. So I should say three center, and there were only two electron bonds, right? Three center, two electron bonds. Okay, because no extra electrons were coming initially. The electrons which were there in boron hydrogen bond, they were only getting stressed to another boron. But in the presence of NH3, they separated because NH3 was ready to form bond by giving its lone pair. So that is a better option. Okay, right? So suppose if we heat it, these two molecules join together and they form B3N3S6 and hydrogen gas will come out. This is known as borazine. Okay, suppose you react with ammonia, they separate, two molecules break away from one another, and when you heat this whole thing, you get borazine. Borazine is actually very important because it is having a benzene like structure. Benzene structure, you know, Fatima? What's special about benzene? Can you tell me? Yeah, Fatima. Benzene actually is C6H6. You know what is a special thing about benzene? If you don't know, just tell me, not a problem. Yeah. What is just you can tell me, not a problem. If you don't know, okay. Benzene, there are 6 carbon atoms forming a ring, okay, and they have double bonds. And those double bonds are, there is double bond, single bond, double bond, single bond, okay, 3 double bonds, and those double bonds being neighbor to each other, they join together, and the 6 pi electrons which are there, because they are in a circular manner, their electron density join together and it forms a ring. Okay, cyclic manner they form a ring, right? So in the same way, here we do not have any carbon, but they join together. Okay, how they join together? Like this. Okay, think that boron was having a lone pair, sorry, vacant orbital. I have put an empty box over here, right? And the NH3 was having, how this bond is formed. Okay, NH3 was having extra electrons which are unbonded electron lone pair. So what I will do, I will give a lone pair to boron. Okay, NH3 is there with the filled electron, boron was there with the empty orbital. What they will do, ammonia will say, okay, let's make a bond and use both of my electrons to form a extra double bond which is known as pi bond. Okay, is it clear? This is known as dative bond or pi bond. Okay, is it clear why I put an arrow, Fatima? From nitrogen to boron, why I have put an arrow? Clear? And what this arrow signifies? This arrow tells us that the nitrogen is giving its lone pair to boron, right? So now again we have a same kind of situation which we have seen in benzene, where you had 3 double bonds, okay, because of the carbon. Here also you have the same thing. Okay, you will be studying it in school also, hydrocarbon, and I will also teach you benzene. So these double bond, actually their electron density can combine together, okay, and it can keep on rotating. So I can write it as like this. Are you getting it, Fatima?
Yes, sir.
Okay, so the same situation we observe in benzene also. Like this one. So I put a circle to denote that the 6 electrons are moving in a circular manner, and this is borazine. This is also known by, because it is exactly same as that of benzene. The electrons are same. There are alternate double bond and single bond, and the electron density of the double bond become homogeneous. It's keep on moving because they are adjacent. They join together and it's keep on rotating. So this is borazine, and it is also known by the name, because of its resemblance to benzene, it is known as inorganic benzene. It is known as inorganic benzene. Okay. Inorganic benzene is borazine. It is having a structure similar to benzene, having alternate double bond and single bond. And these double bonds combine together to form a cyclic donut shaped ring of electron. Okay. And it is known as inorganic benzene. Okay. Is it clear? Any doubt in this?
No, sir.
Okay. So, but if we take them in excess and heat, suppose if you take this B2H6 and if you take ammonia, and if you take both of them in excess and heat together at a very high temperature, excess, right? What will happen? They will form boron nitride, BNX, which boron nitride was having a structure similar to graphite, a layered structure. Okay. So it is having structure similar to graphite, right? And it was having a sheet-like structure. That's what we have seen. So you can make this. We have seen it over here. So you can react boron and nitrogen, and you can form this graphite-like structure, which is graphite. Where you use graphite, which is a common thing used for writing, and that uses graphite. Tell me. Yeah. In the pencil lead, okay, graphite is very soft. Okay, pencil we write, the lead is there, that is not a lead, actually that is graphite. Okay, it leaves a mark, it is soft. So this also, this is actually graphite sheet like structure. The sheets are there, they can slide on one another, but it is inorganic graphite because it is not made up of carbon, it is made up of boron and nitrogen. Clear, Fatima?
Yes, sir.
Yeah, okay. Is it clear? So just go through it. If there is any doubt, please tell me.
No doubt, sir.
Okay, just remember what is borazine and all. Okay, so now let's move ahead, right? So this is important. So this is inorganic benzene, inorganic graphite. So now let's move ahead. Okay, and let's talk about some other reaction. Okay, and other reaction, suppose this diborane ammonia reaction you have seen. What will happen if you put ammonia in this diborane? They are going to break away, and they are going to form BH2NH3 whole twice plus and BH4 minus, and once you are going to heat it, it is getting converted to inorganic benzene. And if you take them excess and heat them together at very high temperature and pressure, they are going to form inorganic graphite. Okay. Now another thing is, what will be the reaction with oxygen? Oxygen, it will burn and it will form B2O3. Right? Okay. So B2O3 will form, and this B2O3 is boron oxide. It is burning of B2H6. Okay, just like the ethane. What is the formula for ethane? Tell me, Fatima. It is ethane is C2, yeah, H6. Okay. So if the ethane is C2H6, borane is B2H6. But there is a difference. Ethane has complete number of bonds, complete number of electrons, but borane doesn't have complete number of electrons. So that's why it reacted with NH3. Okay. So it is going, if you burn it with oxygen, it is going to form B2O3 and it is going to form H2O, water. Like in ethane, if you burn it, or methane, if you burn it, it is going to form CO2, oxide of carbon and water. Borane, if you burn it, it is combustion of borane. It is going to form the oxide of boron. Okay. And it is going to form, okay, it is going to form water. Okay. Is it clear? B2H6, if you react it with alcohol, means you can take any alcohol. Let's take C2H5OH, 6 molecules, right? So B, this is ethyl group. Okay. How much you are comfortable with organic? Tell me. Yeah, Fatima.
Yes, sir.
How much you are comfortable with organic chemistry? Yeah. Tell me.
I know.
Yeah.
I know most of it.
Pardon?
I know some of it.
Okay. No problem. We will cover it in detail. Okay. Do not worry. So you can put ethanol. Ethanol has this H plus acidic hydrogen which comes out, and this H plus is going to combine with this H, and they are going to form 6 H2 molecules. I will write it as 6. Okay. Yeah. The hydrogen from the alcohol and the hydrogen from the borane, they are going to join together and they are going to form H2 gas. Okay. And where these 6 O and ethyl, this is ethyl group, OET groups are going to go Each boron is trivalent, so each of them are going to join with boron. So that's how we are having this, right? Clear? So this is the reaction. Now there is one more compound, which is borax. Okay, let's have the structure of it. That is important. The structure of borax. Borax is a white powder. Okay, have you heard of borax? Where it is used? Any idea? Tell me, Fatima, where it is used? Borax. Any idea if you have? Actually, borax is a white powder, or which consists of boron oxides, right? So borax is having a formula of, it is used for the purification of gold. It is having formula Na2B4O7.10H2, or if I mention it in detail, it is having a formula of Na2 OH4. This is the formula of borax. That is a white powder. It is used in eye wash. It is used as an antiseptic. Okay. So just have a look at the structure of boron. So there are four boron atoms. Okay, and there are 4 OH. So what you can do is you can connect each OH to each of the boron atom and put oxygen in between. Make a ring out of them. That's how you can remember. Okay. Make a ring out of it, cyclic ring, in which each boron is connected to oxygen, then boron, then oxygen, then boron. Okay, make a ring out of 4 boron atom. Put OH on each one of them, because there are 4 oxygen atoms. Okay, but there are 5 oxygen atoms, as you can see over there. So 5 oxygen atoms, 4 of them we have put in the middle, in the ring. So where you are going to put the 5th one? So 5th one you can attach diagonally. Okay, make a ring out of it. You can attach diagonally. So it is going to have minus structure. Okay, Na plus, right? So this is going to be the structure of borax, right? And these are called water crystallization. Water crystallization means they are not connected to this borax unit. They are actually present between the cation and anion. So this is the cation, this whole thing is an anion. Okay, and they are present in between them. Clear? Any doubt in this?
No, sir.
So to remember this, how to draw borax, okay, little bit it is required. And now this is the let's talk about one more compound which is very common, that is S3BO3. We have seen its preparation, okay, in the starting. This is a structure. So here also what happens is this boron, borax, this orthoboric acid units join together. This is boric acid. This is layered structure. White slippery solid powder. Okay. So where do you use it? There's boric acid, solid. Yeah, tell me. Fatima.
In laundry.
In?
Laundry.
Yeah. Very good. And in carom, when we play, we put some powder. Have you seen it?
Yes.
So that powder makes the carom surface, carom board smooth. That is white slippery powder. Okay. And that is your this solid borax. Okay, solid orthoboric acid. Okay, it is having a slippery structure. It is having a slippery structure. Why? Because these units join together, and they join together and they form a layers. So whichever the solid is having a layered structure, there you have, wherever you have a layered structure, there you have this kind of thing. The overall solid appearance will be white slippery powder. We have seen it in boron nitride, which was a layered structure. This borax, orthoboric acid, not borax. Borax was not having layered, but it was having a cyclic structure. This orthoboric acid is having a layered structure, so it is a white slippery solid. Clear? So this is all about the important compound of boron. Boron, actually, these are electron deficient, so actually they exist in the form of triangular units, and those triangular units can join together because they are electron deficient, and they can form polymeric structures, right? And this borax, actually, it is used in laundry. Yeah, you said it very correctly. This borax, actually, it is used in antiseptic also, mild antiseptic. Okay, clear? So is that clear? Any doubt in this?
No, sir.
Okay. And orthoboric acid, that is clear. Now let's move to, so this is because of the hydrogen bonding. Hydrogen bonding, you know. What do you mean by hydrogen bonding? Yeah. Fatima, tell me.
Can you repeat?
Pardon?
Can you repeat what you said?
Actually, these are joined together by hydrogen bonding. Do you know what is hydrogen bonding? Actually, the edge of OH is getting attracted towards the negative charge of oxygen, and this is known as hydrogen bond, right? So why these borax, actually in solid boric acid, These units form a layered kind of structure because they join together by hydrogen bonding. Clear? Is it clear, Fatima? Any doubt in this?
No, sir.
Okay. Now let's move to the uses of these elements. Okay, what are the uses? Can you tell some of the uses? Though we have discussed the uses. What is the uses of boron and aluminium? Yeah. Can you tell some of the uses? Aluminium. Uses of boron and aluminium. Boron actually is used in control rod of nuclear reactor. So boron actually is having a large, the atom of boron is having a large surface area. So whenever you have a nuclear reaction, you put boron rods. Okay, to control, to go that that actually because of the large surface area, these boron atom accept neutrons. Okay, they block the neutrons and they don't let the nuclear reaction go uncontrollably. Otherwise a nuclear explosion will happen. Okay, so these boron rods are used as control rods in nuclear power plants where they control the nuclear reaction. Okay, aluminium is very light. Aluminium is used to make lot of things in daily life. Okay, we use lot of aluminum foil for packaging. Okay, and aluminum is used to make an alloy to make aeroplanes. It is very light and strong, so it is used to make aeroplanes. Aluminum and mixed with magnesium, right? The next thing is boron. We have seen borax. Borax is used in glass. So laboratory glassware, have you seen? In lab we have a glass that whatever the beakers are there, whatever the flasks are there which we use, they are made up of boron glass. Why they are made up of boron glass? That is called borax glass. Okay, and that is actually pyrex, or it is also named by the commercial name of pyrex. So why do we use these glasses? Because they can withstand high temperature. Suppose in lab if we are heating or cooling, okay, so these glass can withstand high temperature. So there you use boron. Boron nitride actually it is having a polymeric structure. So it is used to make bulletproof jackets. Okay, so the pyrex glass. Okay, clear? Remember this name, pyrex glass, and it is made up of boron. Okay, and boron control rods, right? That pyrex glass is a heat resistant glass. Aluminium is used to make aeroplane structures, which is light. Okay, aluminium is used to make a lot of things for packaging, right? Now the next thing is diagonal relationship. Okay, so which and anomalous behavior, which elements will show diagonal relationship and which element will show, first of all tell me which element will show abnormal properties as compared to the rest of the elements of the same group. In group 13, out of boron, aluminium, gallium, indium, thallium, which element will show abnormal properties? Tell me.
So, boron.
Boron, yeah. And what is the reason for anomalous behavior of boron?
Because it's a non-metal
Yeah,
and it's small in size.
exactly. Anomalous behavior of boron. It is a non-metal. Rest all are metals. Okay. Like aluminium is a metal, and the metallic character increases down the road. Boron is having a small size. Very true. So what happens with the small size? What all side effects are there? Tell me. Yeah. It is not going to lose electrons easily, and from because of the small size, it is having high ionization energy. High ionization energy means the boron cannot ionize itself. It doesn't form ionic compound. It does not form ionic compound. It can form only covalent compound. Okay. While the rest of the elements can form ionic compounds. Like we have seen AlF3, Al2O3, aluminium nitride. Why it doesn't form? Because of its high ionization energy. Okay, clear, Fatima?
Yes, sir.
Rest of the elements, aluminium is there, gallium is there, indium is there, helium is there. They can form ionic compound. Okay, and what else? What could be the other anomalous behavior of boron? Tell me. Yeah. Inability to make what? 4 bonds, right? Boron, more than 4 bonds. In boron can't make more than 4 bonds. Okay, clear? Because boron is a second paired element, so can't make or can't exceeds its tetravalency. Can't make more than 4 bonds. Is it clear, Fatima? Why it can't make more than 4 bonds? Tell me. Yeah, because it doesn't have any d orbital. Okay. It is a second paired element, and second paired element, if you have, That second paired element has only 2s and 2p. So out of this 2s and 2p, they are having 2s is having 1 orbital, 2p is having 3 orbitals. So it can make 4 bonds only. It cannot make 5 bonds. Can't make more than 4 bonds. It cannot exceed its covalence. Is it clear, Fatima? Any doubt in this?
No, sir.
Okay, so these are some of the properties of boron. Now, I think this group is almost complete. Just we will look at some of the diagonal relationship and then we will move on to group 14, which is carbon family. Okay. So I hope it is clear. Do share if you have any doubt, anything which is not understood. You can ask me later also, not a problem. Okay. Though you have idea, very good idea of the things. So need to just little bit brush up concepts and remember some key points which are discussed with you. Okay. So let me end today's class and let's meet in the next class. Okay. Bye bye. Take care.
Bye, sir. Thank you.
Okay.